Hi guys, this is the fourth attempt I'm trying to turn on this stream. If this time it won't work, then I think we are going to reschedule because honestly I don't know how to fix it. So nevertheless, this is the fourth episode of Quantum Programming Livestream. I have no idea if you guys can see me or if you cannot see me because I just keep restarting this thing over and over again. So yeah, today I planned we could talk a little bit about quantum teleportation, but I'm not sure if that's going to work out based on the technical issues we are facing here. So if you guys are still there, perhaps you could write something in the chat so that I know you guys can see me or not. Let me also write something. Test message. It appears that my message goes through. Yeah, so quantum teleportation, that's what I planned for today, which might actually not really work out. Yeah, I don't know if we can actually pull it through. Let's just wait a few more minutes, see if someone appears online. Let me just check my phone if there is someone here. This is so stressful. Anyway, whatever. Yes, Manish, it is a technical issue. So, can you see me well now? Can you tell me if you can hear me and see me? That would help me if you tell me. And I will just keep talking in the meanwhile. So, quantum teleportation is a quantum algorithm or a protocol that allows you to perform teleportation of a quantum state. And why is it called teleportation and not just... Okay, good, stable. Thank you, Manish. Glad to know it. And why is it called teleportation and not just copy or move something from place to place? We are going to clarify soon. But before, let me pull up a little advertisement, as usual. So there are some videos by Tim about quantum teleportation. His lectures are up online. So if you want to go more in depth and be more technical about it, I recommend you to check his lectures and also his mini lecture series. Where's the other one? This is the other one. So I will provide you with the links in the description to those lectures. And there's also a cool video by Manish who is in the chat, which I will show you a bit later. And let me just prepare myself something to drink. I have two glasses shapes, not sure which one to choose. Tulip or Duvel. I think I'll go with Tulip today. In the meantime, I'm monitoring the dropped frames rate. Hopefully it will not increase and we could just continue. So yeah, now it is the real quantum programming live stream. My whole desk is covered with beer, but that's fine. So I have prepared some... so first, this talk is going to be divided into two sections. In the first one, we are going to talk a little bit about the classical bound of how much you can estimate a state based on measurement given you have n copies of the state. And this will show us what motivates us to have quantum teleportation. And after that, we will jump right into simulating quantum teleportation. So let me just pull up a new file right now. which is episode 4A. So first, let me just clarify a bit that if you have, there is a known theoretical result that if you have n copies of the state, in average, you cannot estimate the state better than n over n plus 1. So if you have only one state, the best you can do, sorry, n plus 1, and n plus 1 over n over 2 or something like that. All right, that's embarrassing, I forgot. But for the 1 qubit, that's like 2/3, okay? So I have prepared little, hold on, first let's cheers. Cheers, guys, let's hope this stream works out. So I have prepared some Alice and Bobs here, so that we can demonstrate the protocol. These are the qubits, just ping pong balls. And I have some actors. And this one. Let me just change view. Hi, Mom. Mom is here. Hi, Mom. You found the link. Great. So let's. Normally, people use them to call them Alice and Bob, but we are going to call them Howard and the TerrorCon. So let's say that the TerrorCon has a qubit, and Howard tells him, "Hey, TerrorCon, I want to remember this qubit, you know, last week. Can I have it? You told me you will have it." "Yeah, sure, but you know, I'm on a trip. I can send it. I can just send it to you." "Okay, fine. So how many copies of it do you have? Because I want it done accurately." So apparently, according to this whole n over n plus 1 or n plus 1 over n over 2 formula, the only way you can actually guess the state properly is you would need to have infinite amount of copies of this state, right? Let me just check my phone because it seems like we lost a few people. I will just send a quick message to Adam because he was here. Adam. Back online. Alrighty, and I'm back, right back here. So guys, imagine like this dude, he has a qubit. And he is allowed, and he is allowed to perform only one measurement, okay? And based on this measurement, he has to guess what the state is like. So what would be the protocol that we would do? Like imagine you can measure this qubit only once and you have to sort of guess what this qubit is. That's, yeah, pretty difficult. So the reason why I painted half of this ping pong ball in blue is because my idea for doing this, so we are going to demonstrate this 2/3 classical bound. So you have this qubit and you decide to measure it. You have to choose in which basis you measure. So you can use, you know, Z basis, X or Y. And when you measure, you get like either +1 eigenstate, either -1 eigenstate. And this allows you to sort of guess on which side of the block sphere you are. And the rest is just, you know, a pure guess because you have only one measurement, so you can just choose some direction, perform some perturbation, and just pray for the best. That's why half of the ball is painted blue, because you just sort of choose sides of the ball in one of the directions. Oh, hi, Dad. Dad is here. And then we can perform pi/2. So let's say this is Z. Then we can perform pi/2 perturbation in any axis orthogonal to the axis we currently do. And then another perturbation from 0 to pi within the axis that we are measuring. So let's try it out and do it. So, okay, let me just pull up my notes. So, yeah, so what I just said was pick a measurement basis. Then we are going to, oh, the frame drops is pretty high. I hope you guys can still see me. Then we are going to perform orthogonal perturbation. Then perform perturbation around the measurement axis on the state that is equivalent to the eigenstate that has been measured. And this is our best guess. Then we get fidelity, and then we pray for the best. So let's say that our measurement, hold on. So as usual, we will need numpy as in p, and from qtip, let's get, well, we will need states, so we need basis. We need basis, and we are going to do some randomness. We will need a random state, which will be our state we are going to be estimating. The internet connection is so bad. Half of the frames are dropped right now. So this is for the states. Now we are going to be needing the perturbations. And RZ, these are the unitary operators. Then measurement axis operators. You guys can still see me because the frame drop is crazy. Let me just type in the chat. Can you guys still see me? Okay, whatever. I'm not going to get. I'm not going to get nervous. I refuse to get nervous. I must not fear. Fear is the mind killer. And the measurement. Expect. So let's say that the measurement basis is like. So hold on. Let me just copy some states from the previous code to save some time. So of course we will need these. Is everything okay, Manish? Unfortunately, I cannot see emojis. When you guys send emojis, I cannot see them. They do not get rendered properly. Okay, you see me. Good. Thanks, Dad. I hope the recording is going to be fine. Worst case, guys, worst case, we just do it again. Let's not get upset about it. Hold on. Plus I. Negative I. I can see well. Great. Thanks, Manish. I appreciate you telling me that. So the Y eigenstate basis we're missing. Let's just make them. Oh, I'm editing the wrong file. Shit. Should be here. Tim is not here. I guess he forgot. Minus IJ. Oh, thanks, Adam. Thank you, guys. You guys are very helpful. So, okay, the protocol was like we grab, we measure in a basis, then we perform some perturbation. Let's do it. So, let's call it an experiment function. So this will simulate our little experiment with a single copy of the state, which will accept a state that is being estimated, a measurement basis, a zero eigenstate, plus one eigenstate of this basis, minus one eigenstate of this basis, orthogonal, orthogonal? Yes, orthogonal perturbation and origin perturbation. Quantum corrections, yeah. Quality is getting worse and worse of those streams. I really can't believe you guys can really see me because I have like 14 kilobytes per second in my network right now, which is super bad. But anyway, I'm not going to stop now. I started and I'm doing it. So yeah, we have this, and we are going to perform those perturbations. So first of all, let's make some random angles. Random, uniform distributed between minus pi and pi, because we want to stay in this blue region, because we don't want to go, you know, if we want to stay on the side of this eigenstate we measured. So it goes only between minus pi and, sorry, pi over 2 should be. Pi over 2. And here, pi over 2. And we just want one measurement. And we take the first one. For the other one, we can go all around. Because once we have a point somewhere here, whatever we rotate here, we will still say it on the blue side. So anything between 0 and pi will do. So let's just go between 0 and 2 pi, all right? That should do it. So let's prepare the operators for that. So there's going to be rotation, the orthogonal rotation, rs of phi. This angle should be theta. Just pull up the chat so that I can see what you guys type at the same time, that I don't miss any message. Okay. Another perturbation, Rho of theta. Okay, so now we simulate measurement, and you guys, let's measure. You guys remember how we measured last time we simulated the measurements, right? So it's absolute value squared. So we measure, yeah, the expectation value of the chosen basis squared. Whoa. So that will be a number between 0 and 1, right? So if it is, if p is above 0.5, then cat init is the, should I call it? Yeah, that's going to be psi 0, right? Otherwise, cat init is psi 1. I think that works. And now we apply those perturbations. So first the orthogonal. So that's going to be rot s. And then the one in the current basis. Alrighty. That works. Now we get the fidelity. So that was absolute value squared, right? Overlap between this and the state that we received. And let's just skip the praying. So that's our experiment function. Let's pull up some plotting. I made a function called nicebars that will help us plot it. Dropped frames 60%, getting worse and worse. I think this stream is going to be trash, but fine. Guys, I don't know what to do. I don't know what to do. Okay, so there are 3 possible choices, right? The first variant, second, and third, because there are 3 possible bases. So let's just define them. So the first one is going to be, we measure in sigma x basis. We have the plus state and the minus state as the +1 and -1 energy eigenstates. We rotate Rx in the current basis and Rz in another basis. Ry would work as well. It doesn't matter really. So wait, Rs is, let's put them in the reverse order. So this is going to be first orthogonal and then current. Var 2. This is going to be sigma y. How did we call it? Did we call it cat IP and cat IM? Rx, why not, and Ry. And lastly, the third variant is going to be sigma z. And of course, cat 0, because there's 0 state, cat 1 is the negative 1 eigenstate. Orthogonally, we can do Rx and Rz within the given measurement basis. That's good, that works. We are going to store the values, the measurements averaged out, label them somehow. And finally, let's repeat the experiment. First run is going to be like 10 times, and 20, whatever, 40, 80, 160. I think that's enough. So every time we perform the experiment, we are going to do for n, which is the number of times we try to guess a different state. That's very important. Range n. Was it n? No. Ensembles. Okay. 65% frames drops. This stream is going to be crap. I don't know what to do, guys. I don't know what to do. I miss the good internet days. So we repeat it 10 times, right? We take a random 2-level cat, which Qtip will provide us, and we just prepare the arguments for that function, right? So let's do it like this. So there's going to be m, then psi plus, psi minus, rs and ro. This is going to be, let's grab the random one, random choice of the variance. That should do. And we just use our function to get the fidelity. This one, the experiment function. Yeah. Yeah, Manish, I see your message. Oh, guys, I need more beer. So, yeah, this is the fidelity. And we are just going to average them out, basically, just to prove that it will never go above 2/3 in average. So we just add the fidelity. Later, we just calculate the average, right? Nothing special. We add it to our results. And then we label it just to have something on the plot. Just to know how many times we did it. Let's just plot it. Maximum is going to be 1 because it's a probability. Let's draw a line, horizontal line on 2/3 for the reference. Let's title it Classical Bound of Teleportation. File name is result.png. That should do the trick. Right, I wonder if it runs. Huh. Where am I? Okay, I'm in a good place. Let's just run it. Episode 4a pi. Oh, invalid syntax. Jeez, I wonder why I forgot this comma here. It's impossible, it will just run. It must be a problem. Ah, okay, okay. Var. See, I'm a human, I made a human error. Machine would never make such error. Psi 0 is not defined. That's normal because it's called psi plus and psi minus. Another human error. Deprecation warnings, we don't care about them. We got some results, so let's just open them up. There should be a result.png here. Yeah, so guys, you can see never above 2/3. Stays at 2/3. Hold on, let me just label that this is 2/3. How to do that? It's going to be like that. H line underscore text equals 2/3. So who knows? Maybe it is just blind luck. So let's just do it again. Let's just do it again. I mean, maybe we were unlucky. Jeez, we can't go above 2/3. I wonder why. See, guys, it's impossible. Like, it has been proven. It's a theoretical result that for one copy of the state, you cannot go above 2/3. That's just the best you can do in average, of course. So if this guy wants to send his qubit, that guy needs quantum teleportation. And that's what we are going to talk about now. So let's just pull up, maybe yesterday I drew a little graphic for you. The quantum teleportation, supposed to be here. Where are you? Teleportation. And here, let's open a new file. New file. Just do like this. So we are passing to the part B of this talk. Well, I'm puzzled. Guys, I'm still sleeping. Sorry. Yeah, got it. So here on the top left, you can see the teleportation quantum circuit. So we have 3 qubits. The first qubit contains some state that is going to be teleported to the 3rd qubit. The first 2 sections up to psi2 prepare the entangled pair of qubits between qubit 2 and qubit 3. And by psi4, the first qubit is teleported to the 3rd qubit. And the reason why we can say it has been teleported is once you reach psi2, you no longer need any interaction between the first 2 qubits and the 3rd qubit. You can separate them whatever the way you want. You can put them on the other sides of the universe. It doesn't matter. It will still work. And it will work instantaneously. There will be no time delay in performing any operation by the time you reach psi4. Although later, as you can see, between psi4 and psi f, I thought it's 7, you need some corrections. I will explain that soon. But we are already 30 minutes in the live stream, so let me just get going and let's get this thing started. So first, whoa, why do I open the Groundhog Day? Anyway, but that reminds me to say hi to Bill Murray. Hi, Bill Murray. How are you doing? I hope you're watching us. We miss you. We wait for you to join our stream. Where is this teleportation file? Bill Murray, what did you do again? There you go. Bill Murray really wanted us to see him. So let's do it. We grab NumPy as usual. Do we need anything random? We don't need this. So, okay. we will need a random state to be teleported. We will need to prepare our own states. And now we have 3 qubits, so we will need a tensor. That's for states. Then, okay, I look at the gates on the circuit, and looks like we will need Hadamard, C0, X correction, and Y correction. So that's the unitary. Let's also grab the expectation value. I'm not sure how I'm going to perform the measurement. For now, maybe don't need it. So, yes. So, first, we will create random state. Then we will initiate the circuit in something like psi tensor. This is tensor 0, 0. Okay, perform the circuit. So this is just to reach the psi 4. Then we are going to simulate the measurement, right? I think I'll use the projection operators for that. Then we are going to apply the classical corrections. Get fidelity, just so that we can plot something. And plot the result. Guys, I already know why the quality is so poor. Hope you guys can see me. 68% frame drops. This stream is going to be trash. I will have to do it again. Hate my life, hate my life, hate my life. Whatever. Psi. Random, roundcat, right? Roundcat, 2-level system. Initial state. Okay, that's easy. Psi 0 equals tensor of psi basis 0 and another basis 0. That works. So now let's just do one by one, okay? So bear with me. Psi 1. We apply the Hadamard gate, right? So Hadamard gate times psi 0. And there are 3 qubits in the system. The target is qubit 1. The indexing starts at 0. Psi 2. This is the C0. Psi 1. We are reaching 70% frame drops. Wonderful. Wonderful. So the first qubit is the control qubit. The target qubit is the qubit number 2, starting from 0, of course. Psi 3, that's another C0. This time control is 0. And target is 1. Then psi 4 is one more Hadamard. Just target. It's a single qubit gate. Okay, so by now the qubit 1 should be teleported to qubit 3. For the measurements, we need to consider all the outcomes of M1 and M2. Let's just do it. So let's call it configurations. It's going to be a list of, do we have, wait, let's grab some intertools. That's our favorite module. Product of, we can only measure 0 or 1. We repeat it twice. Hold on, I have some message. Let me just check. Guys, I think it's just not working. I don't know. I see 70% frame drops. I just got a message from my mom that it interrupted. I think it's pointless. I think I will try to do it again for you guys. So I'm really sorry, but I'm just going to stop the recording right now. And I hope you will join me again. I don't know what to do. Honestly, guys, I don't know what to do. I'm so upset right now. Okay. Sorry, guys. Due to technical issues, I have to stop the stream. I hope you will have the patience to do it again with me. Yeah, I don't know. I don't know what's the problem here. Okay. You know what, guys? I decided I will finish this stream. So I stopped it because I felt angry and upset, and I have this rule that I really want to be authentic. I don't want it to look like I have cut something in the middle or edited it. But I realized that actually if I stop because I feel upset because of technical issues and poor internet in China and stuff like this, then I'm actually hiding something from you, and I don't want to do that. I want this stream to be about authenticity, about being authentic and being true and being real. So we are going to finish it. I'm going to finish this teleportation for you guys. I'm not going to remove anything I recorded, and I will just join the two recordings, and we are going to upload it the way it is, and it's going to be fine. It's going to be good. So bear with me. Let's do it. Let's have this teleportation going. So we produce all the possible outcomes of the M1 and M2 measurements. And in our Psi4, we have the final state. State that is teleported. So to simulate the measurement, we need to project those possible configurations, right? So let's make some projectors, okay? Let's make some projectors. So here I will store the projectors. I hope everything works. Yeah, guys, sorry I'm so upset, but I'm so easily irritated, you know. Life is just so hard during the pandemic, and I don't want to blame it on the pandemic, but there's just so much shit going on. But yeah, the stream is about being authentic, and I am going to be authentic. I'm going to be the real me in front of you guys. So the projection operators basically ensure that sort of when we apply the projection operator on the state, it removes the subspace projected by the projection operator. And that simulates measurement really well, actually. That's a very simple way to simulate the measurement, simpler than using tracing. That's actually my favorite way. The only problem here is the bookkeeping. And of course, we do not want to project on the, oh yeah, we need identity. Of course, we do not want to project on the teleported state because that would destroy the teleported state, right? Let's do it. I'm going to finish it alone. I don't think you guys see that the stream has restarted, but it's fine. I really appreciate you guys went online with me. I'm really glad. Simulate measurement. So now we need to produce exactly 4 states, right? We need to produce 4 states because there are 4 possible measurement outcomes of M1 and M2. So yeah, so let's call it the projected states. And we just do it for every projection operator. For P in PS. So that is going to be just P applied to Psi4, right? And I believe we need to normalize it, or renormalize it, rather. And we just add it to the list. I don't have any video editing software. I wonder if I can just join those 2 files somehow. I hope I can. Maybe FFmpeg can do it. So let's apply the classical correction. So x is going to be Rx by angle pi. And z is going to be Rz by angle pi. And yeah, so let's just check for which outcomes we have to apply it. So these are going to be corrected states. So for the 0, 0 outcome, we don't apply x and z because you can look at the lines connecting the measurements to the operators, correction operators between Psi4 and Psi-F, and whenever the measurement is 1 or up, it will apply this operator. So for the 0, 0 outcome, nothing gets applied. That's just identity. So we just grab Psi-proj first one, right? Because that's the 0, 0. Then for the second one, 0, 1, we only apply x. For the third one, 1, 0, we only apply z. And 1, 1, we apply both. Order is very important. So the circuit goes from left to right, but the unitaries go from right to left. So that should be Zx. Okay. Right, looks good. So what now? We need some So we will plot simultaneously the outcomes with correction and without correction. So hold on, how to do it? We will need to prepare. We will need to sort of produce the reference states to have something to take overlap with. Produce the reference states. Let's call it psi-ref. And it's going to be basically in we do all the configurations, right? And the reference is basically, that's just going to be the measurement outcome and the expected teleported state. So we just expect it to be there. So psi-ref, psi, whatever. That's just going to be tensor basis to M1 basis two level M2, and did we call it psi, the random initial state? Yes, it's psi. So that's what we really expect to measure. Okay. Psi-ref, append psi. That looks good. And now we can basically compute the fidelities. I just do it again like this. I know it's not very pretty, but I find it easier to understand when we just keep reiterating. Hold on, how should I do it? Guys, I need one more drink. I need it. I fucking need it. And I said the F word. So bad. So I think we need both the corrected and not corrected ones, right? So for the corrected outcomes, we just take this ref and whatever has been applied to psi core. So corrected fid is going to be corrected fidelities. And also, hold on, let's apply some better naming. So it's going to be fid and fid C. That's really bad naming, but I like it. So for fid, this fidelity, that's just going to be the absolute value of the adequate corrected state, right? Let me just think a bit. There's so many thoughts in my head. So, of course, we need all the configurations. I'm not sure if that will run like this. Does Python support pattern matching like this? I think it does. Oops. Sorry. Guys, I'm so tired. So we have the configuration. We need the corrected state and the reference. So So this is the corrected state, and this is the reference. Just take the overlap between them. Just square the absolute value of that, and that's our corrected fidelity. And thinking how to do the not corrected one. Of course, we will still need the reference, still need the projected state. So we will just take, let me just first plot this maybe. So I have this function, it's from my blog. You can check my blog. There is this whole simulation there actually. Was plot teleportation outcomes. And the way it works is we just do, of course we need title. So impact of classical correction and fidelity of teleported state. And file name equals result.png, that's what we use now. And we just apply plot teleportation outcomes. So we will put fid C. I think we need some labels as well. Labels are going to be basically M1 and M2, so 0, 0, 0, 1. 1, 0. All the possible outcomes of M1 and M2, right? And title and file name equals file name. That should do. So the only missing thing is how to get fid, the uncorrected one. Should I? I just do it without applying these guys, right? So I just use proj. I do the same thing as here, but instead of core, I can just use proj. That should do. That should do. Let's do it like this, guys. And actually, I don't really need those configurations here. Let's remove it. Let's just remove this thing. Sorry guys, I'm just so sleepy and also a bit emotional because I'm sort of a perfectionist. I'm not very good at handling failures like this. Sci-proj. Let's call it P. Here we call it P. And we of course have to add it to the list. So this is the corrected one. So fid C append F. And here that is going to be just fid. Fid append F. That looks good to me. That looks good to me. Let's just let's run it and see. episode 4b. Invalid syntax. It's okay. I can fix that. Incompatible QObject shapes. So seems like here we provide something of the wrong dimensions. What's our psi 0? Psi 0 is of dimension 3, which is correct. Let me just think really quick. Which line is it exactly? It's psi 4. Yeah, psi 4. This one has an issue. 3. Control 0. Yeah, 0, 1. Huh. That's really weird because that's totally correct. Let me just print psi 3 and see what we have there. Oh, it's not only there. There is deprecation warning. Deprecation warning is fine. We don't care about that. I should really update my QTIP and start to use more recent standards. Okay, let's see what we have there. Oh, guys, so tough. Okay, the dimensions are 2, 2, 2. Oh, that's an operator. Not a state. No, it's fine. It's fine. Type cat. There are 3 of them, so it's all right. Let me print the previous one. What about psi 2? So weird, guys. You know what? Let me just turn off all those deprecation warnings because I just can't read anything. Category should be deprecation warning. That should do. Let's run again and see. So, and this is line 39. Just enable the lines. Display line numbers 1. 39. Yeah, it's not there. It was fine. Here it was fine. It's later. I'm not going to remove now because that will change the lines. It's here. The problem is here. So the projector. Oh, I know. I just put cats there. Well, those should be projectors. Okay, that should be fine. Now it should be fine. And now let me remove this thing because we no longer need it. Whoa. What is that? Looks like infinite loop to me. I have no idea what that is. Maximum recursion depth exceeded. The first time I see something like that in qdip. I wonder where it starts. The output is just too long. It's crazy. Hold on, I will find it, guys. Don't worry. Reference states, fine. Projected states. Huh. Yeah, this is Psi4. Hold on. Do I renormalize correctly? Yeah, I think I do. I think I do renormalize it correctly. Could that be the list problem? I don't think so, but let's just do it anyway. Okay, same problem. What is that? Where that starts? I have no idea what's going on. I don't have any recursive function anywhere. This is crazy. I don't know what to do. Alright, I'm just going to be commenting things out until it's fine. Let's do it the computer science schoolboy way. Okay. Bear with me, guys. Okay, until here it's fine. So let's just move this thing a bit later. Just move it here. So here we should have our projectors. We just add them to the list. Yep, fine. So maybe it's the renormalization. I'm glad I have more beer. Fine. Operators should also be okay. Yep. Perfectly fine. Oops. I think the beer starts to kick in. Okay, it's here. It happens somewhere here. Why? Why it happens here? Why it happens here? Why is it here? That looks perfectly fine to me. Oh! Okay, got it. I made a recursive list of lists. Now should be fine. Okay. Booyah! Got it. Nice. Hold on, I got too excited and I removed too much. Okay. Fingers crossed. Whoa. We have some problem here. It's fid-c. Now should be, whoa, okay, sorry. Accidentally added this character here. Yep. Okay, let's see the plot. Okay, that's interesting. So just run again for different random state. That's a bit extreme case. Gave us. Whoa. I will explain the plot. I'm just amazed because that's a very okay. Yeah, that looks pretty cool. So let me explain to you. Let me just pull up the teleportation diagram again. So what you guys see on this plot, there are 4 columns. Each of them is composed of 2 bars, and there are 2 colors. So each of the columns composed of 2 bars corresponds to one outcome of measurement of the first 2 qubits. So if you oh, I lost my editor. So if you measure 0, 0, M1 is 0, M2 is 0, then both corrected and uncorrected case is perfect. The fidelity is just 1. However, if you happen to measure, like this guy, he has the first 2 qubits, and this guy, he has the 3rd qubit. So if this guy measures 0, 1, and this guy does not apply X, then he will get 0.2 fidelity. But if he applies X, he will get 1. So in the 0, 1 outcome, the teleportation has worked. The state that he had appeared in his qubit instantaneously, but it is up to a single rotation. He needs to know that he has to apply X to get the right state. And similar for the other outcomes. So 1, 0 outcome, if he applies, so 1, 0 should be Z. If he applies Z, he will get fidelity of 1. If he does not apply Z, he will get 0.678, right? And if he measures 1, 1, he applies nothing, he will get fidelity 0.11. But if he applies XZ, he will get fidelity of 1. So let's just discuss this result a bit, because that's the fundamental thing for the teleportation and why it is being called teleportation is basically the state is already at the qubit psi, or the qubit 3 when we reach psi 4. So the state has appeared there just like that. It appeared instantaneously, regardless of the distances, regardless of the barriers. You could lock the third qubit in the Faraday cage, you could block all the communications, but the entangled pair between those qubits, because the non-locality of this entanglement, the state will get there. So that's why it's teleportation. It will travel at infinite speed. It will appear there instantaneously, regardless of the barriers. That's why we call it teleportation. But there's a trick, and you can see it here. You can see that the state gets there, but it is being changed up to a single rotation. So if you do nothing to the state, you only have 25% chance that you will get the state you wanted. That's why the quantum teleportation allows the information to travel instantaneously to any place at the infinite speed, while even faster than light, But it does not allow faster than light communication, because the person who is teleporting state to someone else needs to perform a measurement and inform this person what correction has to be applied. So that's a kind of disappointing thing in the teleportation, because it is simultaneously amazing and simultaneously problematic. But the reason why we have quantum teleportation is not really related to faster than light communication. The purpose of teleportation is sending qubits to each other. Because as you could see in the first part of this talk, we really could not estimate what the quantum state is without having infinite number of copies of them. And teleportation allows us to bypass that. Like, we just need one copy, and with one single communication, we are able, and an extra qubit, we are able to communicate and move this state somewhere else at arbitrary distance. So that's pretty amazing. That's why we need teleportation. And there are many other teleportation schemes. There are many other teleportation schemes that allow you to basically perform the same protocol in other ways. And I will be happy to show you guys some other ways to perform teleportation. And in the meantime, I think the basic teleportation we managed to perform, and my beer already kicks in pretty strong, so I will just show you the Manish video really quick, and then we're going to finish. So Manish, who was present in the chat earlier, but because of technical issues disconnected and I had to restart, he made a talk about remote state preparation, which is something quite similar to teleportation in many ways. I don't entirely remember what was the difference. I think it was using 2 qubits instead of 3, and it wasn't exactly performing teleportation but something else. But anyway, he is a really helpful guy, so if you watch his talk and ask him questions, I'm sure he will answer and help you understand it better. And in the meantime, I think we can totally conclude, because the level of alcohol in my blood is still rising. So before I get upset again and have before I get upset again and have another emotional breakdown, I think I should stop the stream. I think those streams work definitely better when I'm drunk. I'm willing to sacrifice my health for your entertainment. But for today, I think that's enough. So thank you so much, guys, for your attention. Terribly sorry for the technical issues. I do not know how to fix it. I opened a thread at OBS and nobody has responded. hopefully we can figure it out and have the stream running. So thank you so much for your patience, for your attention. Please consider to like my channel and follow my videos. That is really helpful to me. I would really like to reach 100 followers so that I can choose my own username on YouTube. I would really like that. So I would appreciate if you help me with that. And thank you so much. Take care and goodbye. Cheers.